So when we talk about acids and bases, this is a concept that you're pretty familiar with just through everyday life. We come in contact with things that are either acidic or basic or neutral. And what you have here are three basic definitions of what an acid is and what a base is. We focus on the Bronsted-Lowry definition of an acid, which is something that donates a proton, or in other words, it gives away a hydrogen ion. And a Bronsted-Lowry base is one in which takes a proton, or it becomes a proton acceptor. It takes or receives the hydrogen ion. So we have 6 strong acids and 8 strong bases that we have to memorize. The definition of being a strong acid or a strong base means that you 100% dissociate into ions. So every single mole of a strong acid breaks up into ions, and the same thing applies to a base. Every single mole of that strong base is going to completely break up into positive ions and negative ions. This is called complete ionization, or 100% dissociation. So please put to memory these 6 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid, as well as these 8 strong bases. These are a little bit easier to memorize. They all come from group 1 and group 2 on the periodic table. And it says group 1 and group 2 hydroxides. So just mind the charges of your group 2s. Make sure that you use 2 hydroxides when you're writing those formulas for the group 2 ions. Now, how does this differ from weak acids and weak bases? If strong means 100% dissociation, well, weak means less than 100% dissociation. Weak acids and weak bases partially ionize in water. They partially ionize, meaning only some moles of those weak acids break up into ions. Only some of them are going to break up into the hydrogen ion and the negative anion. And the same thing applies for the weak bases. So you can see here in this picture of a weak acid, you have 5 molecules of the weak acid, and of those 5, only one of them is losing its hydrogen ion or donating that proton. So this is partial ionization. And the same thing applies here for the weak base. You have a lot of weak base molecules, and only one of them is taking or adding in a hydrogen ion, that proton. So if you compare that to the strong acids above, every single molecule of the strong acid HCl is breaking up into a positive and a negative ion. And then the same thing applies for your sodium hydroxide. Every single one of those sodium hydroxides has completely ionized into sodium ions and hydroxide ions. So let's dive into the strong acid versus weak acid a little bit more with some particle diagrams. Here on the left-hand side, I have a strong acid. Okay, we're going to use a generic formula, HA. H is that hydrogen being donated, A is the rest of the acid molecule. And in this picture, we start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 HA molecules. Okay. And I want you to see what happens to those 10 HA molecules. As they ionize, every single HA molecule breaks up into H positive and A negative. So the little atoms, those are your protons, those are the H positives, and then the big green guys, those are your A minus. Okay, so all 10 of those HA molecules have broken up into H plus and A minus. We call that 100% ionization or 100% dissociation. Okay, and if I look at this graph, okay, the concentration of H positive and HA they are both the same. Okay? They're both equal. Okay? Because where did those come from? They all came from the original HA molecule. So in the end, okay, the concentration of hydrogen ion equals the original HA concentration, and that's very important. The concentration of H positive equals the original concentration of the HA, or we can use sub-zero for initial, okay, versus the weak acid on the right hand side. Okay, you have this weak acid HB now, and if I counted all of the weak acid molecules, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 again. Okay, I have 10 HAs. Now when I look on the right hand side, when it dissociates or ionizes, let's circle the ones that have dissociated. Okay. This one has dissociated. Here you have a B minus, okay, and corresponding H positive. So out of all those 10 HB molecules, only one of them, 1 out of 10, dissociated or ionized. Okay, we call this partial ionization. Okay, definitely less than 100% has dissociated, and that is by definition what a weak acid is. Less than 100% of the acid is dissociating. Okay? So strong is 100%, weak is less than 100%. And if I go and look at the graph for the weak acid, you'll notice, okay, now look at that concentration of H positive and compare it to the concentration of the weak acid originally. Here, the concentration of H positive produced is less than that original concentration of acid. And that's because this is a weak acid and so very little of it is dissociating and producing hydrogen ions. So if I looked at some equations now, okay, same strong versus weak. Now we're just going to look at a balanced equation. Okay, here we have our strong acid. Okay. It starts off with that H and that A. And then what we have here on the left, that's water. Okay. And we're dealing with aqueous solutions. That acid is going to give away its hydrogen ion. Okay, that's what makes it an acid. Remember that Bronsted-Lowry definition. Okay, it donates that hydrogen, and that hydrogen, okay, joins the water, and so the water turns into H3O positive. We call that the hydronium ion. And what's left over from the acid is just the A minus. So we have an acid giving away its hydrogen ion to the water. The water in return becomes hydronium ion, H3O positive, and then whatever is left behind from the acid is just the A minus. Because this acid is a strong acid, if I look at this equation, 100% of this is going to dissociate. So the equilibrium lies very heavily to the right in this reaction or this dissociation. So really far to the right. This is heavily product favored because this is 100% dissociation. Okay. Versus a weak acid. Okay. Here we have our HB again. It's going to donate its hydrogen. Okay. Its hydrogen is this little guy here. That's A minus. And when it donates that hydrogen, it also gives it to this water molecule. Okay. The water turns into hydronium again, and then you're left with this A minus. So we have H2O, you have your acid, water's turning into hydronium, and then you have your A minus left over. Okay? But because this is a weak acid, the equilibrium position lies very heavily to the left this time, because at equilibrium, the majority of the acid molecules did not break apart into ions, so you have a way higher concentration. HA is much, much bigger than that hydronium ion concentration. Okay, so we have a lot more reactants than you do product, okay, for weak acids. And so this is why equilibrium lies heavily to the left-hand side. It's very reactant favored because of weak acids hardly dissociate. pH scale is our way of communicating how acidic or basic a solution is. Low pH equals a high concentration of hydrogen, and a high pH equals a low concentration of hydrogen ions. And that's because pH is equal to the negative log of the concentration of hydrogen ions. Okay, so the more hydrogen ions present, the more acidic the solution. The pH does not tell us how strong or weak an acid is or how strong or weak a base is. It is simply the concentration of hydrogen ions, which is due to the molarity of the solution, and then that is also affected by if it's strong or weak, but it's not basic. It's truly not telling you if the acid is strong or weak. We need more information other than the pH to know if it's strong or weak. We need to know how much it's ionizing. So the pH scale, it's a log base 10. So that means if you have two solutions, one with the pH of 4 and the other with the pH of 5, okay, the concentration of hydrogen ions in those two solutions differ by magnitude of 10. So the pH of 4, its hydrogen ion concentration is 10 times greater than the pH of 5. Okay? If you compare pH of 4 to a pH of 6, okay, the hydrogen ion concentration in the solution of a pH of 4 is not 10 times greater than the pH of 6, but 100 times greater than the pH of 6. And that's because they differ by 2 on the pH scale, but because the pH scale is base 10, that's really saying 10 to the second power, which is 100 times. Okay, so we'll go one more example. If you have pH equal to 4 and you compare that to a solution with a pH of 7, they differ by 3, or in other words, 10 to the third power, which is 1,000. So the solution with the pH of 4 has a hydrogen ion concentration of 1,000 times greater than the pH of 7. So now let's practice some calculations of pH. So for pH, you have to be able to use these equations here. Okay? These are ones given to you on your formula sheet. You've seen a lot of these before. pH, yes, is negative log of hydrogen ions. pOH, negative log of OH. And then if I add pH plus pOH, we're going to get 14. Okay, these first three you've seen before. The next two, we haven't gotten to Kw yet, but Kw, okay, is another one of those equilibrium constants, but that W stands for water. It's equal to the hydrogen ion concentration times the hydroxide ion concentration present in the solution, and that's always going to be equal to 1 times 10 to the negative 14. But that, again, because K equilibrium constants are temperature dependent, that value of 1 times 10 to the negative 14 only applies when the temperature is 25 degrees Celsius. Okay. Kw is also equal to Ka times Kb, and we will dive into that a lot more later on in the unit. Number 1 here. Let's calculate the pH of a strong acid with a concentration of 2.5 times 10 to the negative third molar. So this word strong acid, very important because that tells me the concentration of hydrogen ions. Okay. Because I know pH equals negative log of H plus, I need to plug in the molarity of H plus. Okay. Because this is a strong acid, this is the molarity of HA, the strong acid. But we know that a strong acid 100% dissociation. So if this is the molarity of HA at the beginning, then 100% of it is going to turn into H positive and A negative. So remember, when we looked up here, okay, once we have dissociation completed, the concentration of H positive equals the concentration of the HA initially. Okay, so we're going to use that to solve this problem. If the concentration of the strong acid is 2.5 times 10 to the negative 3, then that also means that is the concentration of H plus. So this becomes a plug and chug. You're going to take the negative log of 2.5 times 10 to the negative third. So pH is equal to 2.602. And a word about sig figs and pH calculations. Decimal places count as sig figs and pH values. So look at your original molarity. That's 2 sig figs. So that means I need to keep 2 decimal places in my pH calculation. So we're going to round to 2 decimal places. 2.60 is the pH. Number 2, calculating the pH of a 3.12 times 10 to the negative 5 molar HCl. So HCl, that's one of our strong acids. And this is why you have to memorize those 6 strong acids, because the way we calculate pH for strong is a little bit different than the way we calculate pH for weak. So if it's strong, I know that the molarity of HCl is 3.12 times 10 to the negative 5 molar. And since this is strong, I know 100% of the acid is dissociating, so this is also the concentration of hydrogen ions. So pH is equal to negative log of 3.12 times 10 to the negative 5. I get an answer of 4.5058. And so for sig figs, my original answer has value has 3 sig figs, so that means 3 decimal places. 4.506 is the answer. Number 3, calculate the hydrogen ion concentration and the hydroxide ion concentration of a solution with the pH of 4. So pH is equal to the negative log of hydrogen ions. Okay. So the anti-log or the inverse log would be the concentration of hydrogen is equal to 10 raised to the power of negative pH. This equation not on the formula sheet, so this is very useful to know. I'm going to plug in the pH, negative 4. Okay, so the concentration of hydrogen is equal to 1 times 10 to the negative 4. Now for sig figs, my pH has 2 decimal places. So that means 2 sig figs in my reporting of the molarity of hydrogen. So 1.0 times 10 to the negative 4 concentration is molar. Okay. So for the hydroxide ion concentration, hydroxide would be equal to 1 times 10 to the negative 14 over the concentration of hydrogen. Okay, and I'm using this Kw right here. Hydrogen ion times hydroxide is equal to 1 times 10 to the negative 14, and we can assume the temperature is 25 degrees Celsius unless we're told otherwise. Okay, so 1 times 10 to the negative 14 over 1 times 10 to the negative 4. The concentration of hydroxide is 1.0 times 10 to the negative 10 molar. Now I should be able to do this mental math in my head because the coefficients here are both 1, so I know it's going to be 1.0. And then the difference between 10 to the negative 14 and 10 to the negative 4, that's negative 10. Number 4, calculate the pH of 9.02 times 10 to the negative 6 sodium hydroxide. Okay, so this is a strong base. And since strong acids 100% dissociate and the concentration of hydrogen ion is equal to the original concentration of the acid, same thing applies here for strong bases. The concentration of hydroxide is going to be equal to the original concentration of the strong base. So if sodium hydroxide is 9.02 times 10 to the negative 6 molar, then that also means the concentration of hydroxide will be 9.02 times 10 to the negative 6 molar. So since I have hydroxide, I first have to calculate pOH using the negative log of OH. Plug in the concentration of hydroxide, 9.02 times 10 to the negative 6. 5.04479, and then round for sig figs, i.e. decimal places, that's 3 sig figs. So I'm going to keep 3 decimal places here. 5.045 is the pOH. But they want me to solve for the pH. So pH would be equal to 14 minus pOH. So 14 minus 5.045. And you get 8.955 as the pH. Alternative method for this, since you have the concentration of hydroxide, you could have solved for the concentration of hydrogen using 1 times 10 to the negative 14 over the concentration of hydroxide. And then once you had the concentration of hydrogen, you would do pH is equal to the negative log of the concentration of hydrogen if you wanted to solve it that way. That's perfectly fine as well. So number 5, okay, we're going to calculate the pH of a 2.0 times 10 to the negative 4 molar calcium hydroxide solution. Concentration of calcium hydroxide is 2 times 10 to the negative 4 molar. Calcium hydroxide is one of the strong bases. Okay. So I can know that 100% of the calcium hydroxide is dissociating. The concentration of hydroxide is going to be 2 times this 2 times 10 to the negative 4 molar. And that's because in calcium hydroxide, for every 1 calcium hydroxide, there are 2 hydroxide ions. Look at that subscript there. So the stoichiometry tells me hydroxide is double the quantity of the molarity of the base. So this is 4 times 10 to the negative 4 molar as your concentration of hydroxide. So we can solve it the same way as number 4. pOH would be equal to the negative log of 4 times 10 to the negative 4. We get 3.40 as our pOH. So pH would be 14 minus 3.40, and we would get 10.60 as our final pH. Alternatively, we could have done it this way. We could have taken that hydroxide concentration, okay, and solved, take the hydroxide concentration and solve for the hydrogen ion concentration, 1 times 10 to the negative 14 over that 4 times 10 to the negative 4. 2.5 times 10 to the negative 11 molar for hydrogen, and then the pH would be equal to the negative log of that 2.5 times 10 to the negative 11, and you would have also gotten 10.60. So either way, you have to know the concentration of the hydroxide ion concentration from the given information, and then you either take the negative log of the hydroxide, then subtract your pOH from 14, or you could use the hydroxide concentration like I've done here in red and solve for the hydrogen ion concentration and then take the negative log of that and get your pH that way, you're going to get the same answer no matter which way you do this. So back to that strong versus weak. The reason why we have to know strong and weak differences is because of that 100% ionization. What I've shown you in these calculations, they apply to the strongs. The strong acid concentration will tell you the hydrogen ion concentration. The strong base concentration will tell you the hydroxide ion concentration because 100% dissociation. But when we get to the weak situation, the concentration of hydrogen inside of a weak acid is not the concentration of the overall acid. Remember, this H positive, okay, is so small in comparison to the original acid. So I can't just plug in the molarity of that weak acid into the pH formula because the hydrogen ion concentration is not going to be the same as the overall acid. And more on weak acid pH calculations later on.